So today's fourth day, no? Yes, yes. Okay, good morning, everyone.
Good morning, Dr. Srijit. Am I audible?
Yeah, good morning, Sheik sir. You're audible. Perfect.
Yeah. Oh, thank you.
Good morning, everyone. For this fourth day on recent developments in the renewable energy technology for sustainable development, I, Mr. Harold D'Souza, am very pleased to witness you all here to this FDP. And it's my privilege to address you all on behalf of the EJIT family. I extend my very warm welcome to our renowned speaker, Dr. Saboor, who took time out of his busy schedule and joined us today to be a part of this FDP and share his immense knowledge. We are honored to have you, sir, with us. On behalf of a very warm welcome to you, sir. I also welcome all the participants from various institutes for this FDP. We are very delighted for your presence. Now, on this note, I would like to introduce our today's resource person, Dr. Saboor. Dr. Saboor completed his Bachelor of Technology at SK University, Anandpur, Andhra Pradesh, in the Department of Mechanical Engineering. Completed his Masters in Refrigeration and Air Conditioning from J&T University, Anandpur. He then completed his PhD from NITK, Surat. His area of interest is heat transfer in buildings, building physics, smart glasses for buildings, phase change materials, solar passive buildings, energy efficient buildings, climate responsive building design, solar energy, refrigeration and air conditioning, and alternative fuels. He has vast knowledge in simulation and coding tools such as RefProp, RefLeak, NIST, VCRS, Design Program, Design Builder, Energy Plus, and MATLAB. He has worked as assistant professor at Vignan Institute of Technology and Sciences, Hyderabad, Telangana, and also at NITK, Surat. He is currently working as a senior assistant professor at Vellur Institute of Technology, Vellur, Tamilnadu. He has received several awards. Research Ratna Award of the year 2019, the best research paper, the mentor for the most efficient, fuel efficient prototype car in India, also research awards for the year 2017, 2019, 2020, and the best research paper in the research paper award in 2015, 2016, the best PhD thesis award, also MHRD Fellowship Award, Excellent Master's Thesis Award, and is also a BTech Gold Medalist. He has many patents to his name and also has more than 30 publications in national and international journals. He has also published 5 book chapters and has published more than 15 papers in international conference. He is also a reviewer for many of the international journals. Now, with this brief introduction, I welcome Dr. Saboor for this FDP on recent developments in renewable energy technology for sustainable development. Our today's topic is innovative building envelope solutions for low energy buildings. Sir, I welcome you to this FDP and I request you to take over the session, sir.
Yeah, thank you, Dr. Harold D'Souza, for your kind introduction. I'll just share my presentation. Dr. Srijit, can you make me the presenter? Because here share option is disabled.
Okay, 1 minute. Yes, sir. Now it's enabled. Sorry for that inconvenience.
Dr. Srijit, I am not able to see this again.
Here we have given the grant the permission, sir. It will take a while, maybe few
Okay.
seconds.
Okay.
Dr. Sheik, sir, is it okay now?
Dr. Srijit, I am not able to get share link active now also. So it is showing like a deactivated share icon to me.
Sir, you refresh it. Sometime it will
Okay.
come.
Okay. Dr. Srijit, I have the same issue. I'm not able to share it here.
Here, this side everything's fine, sir. We have granted permission.
Okay.
Settings shows perfect. But no,
Let
no.
me.
When just now we saw you are sharing your screen.
Okay. Okay. Fine, sir. Then I'll be sharing. But I was not audible to you. Okay, I'll try it again in the same way. I
Okay.
hope you'll able to see that.
Sir, now your screen is visible. It's showing that presenting. So you are not audible right now. Screen shows you are presenting. Sheik sir, sir, you are not audible. Sir.
Professor, are you able
Yeah,
to
sir.
speak? Dr. Srijit, his line seems to be not able to hear. Dr. Srijit, I'm audible now?
Yeah, sir. Now it's perfect. Perfect, sir. Now you can start presentation.
Shijit, am I audible?
Hello, sir, you are audible.
Dr. Shijit, am I audible now?
Yes, sir. You're audible.
Yes, thank you.
Only with echo is there, but you just take care.
Yes,
Thank you.
thank you. Good morning, everyone. Sorry for the technical interruption. So, as far as today's topic is concerned, it is innovative building envelope solutions for low energy buildings. So, if you look at the introduction, so buildings consume a lot of energy. According to US Green Buildings Council, so building consume 40% of global energy and they are responsible for 40% of global warming.
Yeah, so audible, sir.
Yeah. Yeah, good morning, everyone. I think there was some technical issue, so I had to sort it out for a very long time. Sorry for the interruption. So as far as the topic is concerned, it is on innovative building envelope solution for low energy buildings. So if you look at the introduction, so buildings consume, why are we concerned very much about the buildings when we have various components or various elements to focus? So buildings consume 40% of global energy, and they are responsible for 40% of greenhouse gas emissions according to US Green Building Council. So if we go on using the fossil fuels for the power production, so our earth temperature will be increased by 10 degrees centigrade and mean earth temperature will be increased by 5 degrees centigrade. Okay, so which causes global warming. Okay, so 40% of global energy consumption also causes 40% of greenhouse gas emission. Okay, so that is the reason why we need to focus much on the buildings. So if you look at the globe, so ice in the Arctic Circle is melting because of the global warming. When the earth is heated up, obviously the ice melts. Okay, so this Arctic Circle ice is melting because of the global warming. Okay, so when this ice melts, what happens is that this ice is actually reflecting most of the radiation falling on the globe. Okay, so when this converts into the water, the most of the radiation will not be reflected back to the atmosphere. It will be absorbed by the earth. Again, it will causes increase in temperature of the earth, which is responsible for again greenhouse emissions. Okay, so we are concerned with the northern hemisphere. The reason is that the northern hemisphere, there is 70 to 80% of the land, and almost 80 to 90% of the population is living in the northern hemisphere. Okay, there is only 20 to 30% of the water in the northern hemisphere. So this is obvious that wherever we human beings live, so there we spoil more. So here we are actually this global warming effect is to the Arctic Circle than the Antarctic Circle. This is the reason. Okay, so there is almost 80 to 90% of the world population lives in the northern hemisphere. Okay, so most of the major countries we can see in the northern hemisphere as well. So if you look at the southern hemisphere, so there is only 20 to 30% land is available. Okay, and we only 10 to 20% population live here. Okay, so there is no problem with the Antarctic ice melting. So we are having the problem with the Arctic Circle melting. Okay, so this is the reason why we need to focus on this. So what is the objective of this particular this kind of building designs? Okay, ultimately to have thermal and visual comfort by reducing energy spent to the conditioning and also spent to the artificial lighting, which in turn reduces the greenhouse gas emissions. So we would have built only one building across the globe having all the elements in it. But the reason is that the world climate is not like that. So we will have different climates across the globe. Okay, place to place the climate changes. Okay, so that is the reason why that we need to focus on various designs. So like design of the building changes place to place. Okay, so the place what we take here maybe in Mangalore may not be same in the Delhi. Okay, that will not be same in the other country place. Okay, so we need to focus much on the building design. Building design varies place to place because of the different season, different climatic conditions. Okay, so if you look at the globe here, so this happens during the June 21st. That is, this northern hemisphere is actually leaning towards the sun. Okay, and southern hemisphere is actually it is far from the sun. Okay, so as a result, this northern hemisphere will have the summer during the season, whereas the southern hemisphere will have the winter during this time, June 21st. Okay, so why do we have the season? What is the reasons for having the seasons? Why can't we have a single season throughout the year? So these seasons are because of the earth axis. If you see the tilt of the earth axis, the tilt of the earth axis is approximately 23 degrees. Because of the tilt of the, suppose if it is completely vertical, we would not have faced such problem. Okay, since it is tilted somewhat, so we'll have that kind of problem. Because of the tilt of this earth axis, we are able to get various seasons on the globe, on the places. Okay, so that is a very, very important point to consider when we are going for the building design. So especially climatic responsive building designs, especially energy efficient building designs, if you are planning, so we have to consider these climates for the design. Okay, so if you look at this side, extreme side, especially this occurs in the peak winter we face on the December 21st. So this northern hemisphere is actually far from the sun. This is the reason why we have winter here. Summer, since it is actually close, see, southern hemisphere is close to the sun during this time, December 21st. Okay, this is completely opposite. Suppose if we are living in northern hemisphere, India is in northern hemisphere. Suppose if we have winter, now winter we have. Okay, so suppose if we have winter here in this space, we have winter. Okay, so during that time, this southern hemisphere people will have summer. Spring and fall, there is no problem. We'll have equal number of days and nights over there. Okay, there is no such problem here. Okay, so we might have studied, or we know from our school days, sun rises in the east and sun sets in the west. Okay, is it actually true? Is it true? No, it's not true. Okay, so sun rises in the east and sun sets in the west is actually true for only fall or spring. Okay, suppose if you take the example of the summer, sun rises in the northeast and sun sets in the northwest. Okay, so if you take the example of winter, especially I'm talking about the northern hemisphere. Okay, so this is with respect to the northern hemisphere as we live in the northern hemisphere. Okay, so if you take the example of the winter, sun rises in the southeast and sun sets in the southwest. Okay, so here we need to focus much on these two things, means extreme summer and extreme winter. Okay, so here you can see, suppose if you focus on extreme winter and extreme summer, peak summer and peak winter, okay, all other days will fall in between. Means we need to focus on this window. This window is called as solar window. Okay, so if we can control this solar window, then we can actually control the solar heat gain passing through the building. Okay, so we have to control this solar window. This solar window plays very, very important role. Okay, so that is very, very important. So what are the different solutions that we have for building cooling and heating? Okay, so as far as these things are concerned, I broadly classified into some categories. So it starts from the building orientation. How are you placing the walls? Whether they are facing east, west, north, south, or southeast, southwest, northeast, northwest, they actually matter in order to reduce cooling or heating loads. Okay, so we are very, very much concerned with reducing cooling loads as we live in country with the tropical climatic condition where the cooling is predominantly major role. So here building orientation plays very, very important role. How are you placing the walls? How are you placing the windows? That actually plays very, very important role in actually controlling the heat gain into the building or heat loss into the building. Okay, the shading, how are you able to give the shading to your glazing systems, especially for the windows? Okay, and how do you have ventilation system for your houses? That also plays very, very important role. Okay, so here also we have various types of ventilation: natural ventilation, stack ventilation, cross ventilation, and night ventilation. Okay, so evaporative cooling, how are we going to attain that evaporative cooling? So we also have some techniques concerned with the earth cooling systems. We also have techniques with the radiative cooling, including nocturnal cooling and radiative reflecting paints. Okay, and also finally we have building envelope solutions. What kind of building envelope solutions that you can suggest to have energy efficiency in buildings? Okay, so what do you mean by energy efficiency in buildings? As I said earlier, we have to reduce air conditioning loads. Okay, so if you can reduce air conditioning load, suppose if you are using air conditioner, we should reduce air conditioning load. If you are not using air conditioner, then we should maintain at least comfortable condition inside the buildings. Okay, so that the occupant inside the building will feel comfortable. Okay, so building envelope solution also we are going to see in this particular topic. So how should be the building orientation? That is also very, very important. Okay, so if you had looked carefully here, see here we have just taken, for example sake, I have taken a rectangular building model. Building model is there. Okay, so here we have 4 walls, 2 walls facing to the east and west and 2 walls facing to the north and south. Okay, so why did we make like this? Why can't we have a north and south? This, if you see, the smaller size, the smaller area of the walls are located towards the east and west. Okay, not on this north and south. If we have north and south, we are actually located the larger surface area of walls. Okay, so why do you have to make it? That is also very, very important here. Okay, and also in the second diagram, if you see, so east and west also, again we have given some space to the states and some space to the other things. Okay, so why do we need to give this? Ultimately our objective is to maintain comfortable conditions inside the building. Okay, so but why are we building like this? Okay, why can't we have n number of options to placing the walls? Okay, that is very, very important. If you had clearly observed here, see here, see this south side, radiation coming from south side. Suppose let us say this man is observing very less radiation from south side. You can see here. Okay, but during winter season, this man is observing lot of heat during the winter season from south. Okay, so what do you mean by that? That is actually the important point to be focused here. Okay, so means during summer we need less heat gain into the building. Suppose if you get more and more heat gain into the building, you will not feel comfortable. If you are using an air conditioner, your air conditioner is going to consume lot of energy. Okay, so means south direction is actually preferable for summer in order to gain low heat inside the building. And see the beauty of this south orientation in the winter. Okay, so winter we need to increase the temperature of the room. Okay, and if you have a large area of the walls or windows towards the south, you will be receiving maximum radiation to keep you warm during the winter. Okay, so that is the beauty of this south orientation. So south orientation is the best orientation for both summer and winter. So during summer you will receive least radiation, and during winter you will receive the maximum radiation into the building, which will provide comfortable condition to the occupants. And if you are using an air conditioner, it's going to reduce the air conditioning load. So that is very, very important. So building orientation plays a major role in order to have the comfortable conditions inside the building. So next we have a building enclosure with vegetation. We can say green facades. So why do we need to focus on green facades? That is also very, very important. Okay, if you can see in this particular figure, so you can see green facades, especially on the terrace of the houses. Okay, so green facades you can see here, green roofs you can see here. Okay, the reason is that, see, if you observe the roofs and walls, see what kind of enclosures we have in the buildings. We have roofs, we have walls, and we also have the glazing system or windows we can say. Okay, so if you observe among all the components, these roofs are very, very important because we are going to receive maximum amount of radiation through roofs. Okay, so we should be able to, suppose if you installed some kind of vegetation, so because of evapotranspiration process which actually happens in a small plant. Okay, so what happens, this roof temperature will be reduced drastically. Okay, so transpiration, like water will be there at the bottom, right? That water will be transported to the various branches of the plant, leaves and other parts. Okay, so from there the evaporation will take place. So it is the combination of evaporation and transpiration both together, that is evapotranspiration. Because of this evapotranspiration, we are going to reduce here the roof temperature by some temperature, 5 to 10 degrees centigrade we can reduce. Okay, and as far as the shading system is concerned, we have different types of shadings. Okay, based on the application, based on the climatic region where you are applying. Okay, so we have a different shading system because to reduce, see, there is a window or there is a glazing system. Okay, the difference between wall and window is clear. So for gaining heat from the wall, it will take a lot of time. But for window, it's not like that. Solar radiation will directly enter into the room. Okay, so we need to block direct to solar radiation. Okay, so that can be blocked with the help of these shading systems. Okay, so we have different types of shading systems: horizontal single blade, outrigger system, horizontal multiple blades, vertical fin, slanted vertical fin, and again. Okay, so that depends on type of orientation, like a window where you are placing, which orientation you are placing the window. Suppose if you are placing the window in the south orientation, first 3 are preferable option to have the shading devices to your window. Okay, suppose if you are placing the window in east-west or east-west direction, then you need to go for this kind of shading devices. Means the heat gain into the building or direct to solar radiation into the building can also be reduced by these shading techniques. Okay. So natural ventilation, this natural ventilation plays very important role in order to reduce the room temperature. Okay. So if you see single-sided ventilation means we'll have a single window. Okay. So air has to come in through this window and also air has to go out through this window. Okay. There is no other option. Okay. That is the reason why most often in buildings, the people prefer cross ventilation, like air has to go from one side and the air has to leave the room from another side. This is the cross ventilation. Okay. Some people prefer the stack ventilation as well. Okay. So here you can see because of the density difference between the air, okay, that is between the hot air and cold air, hot air rises up and just leaves the room from this. Okay. And from this, the air from bottom of the, like, see, since the density is very high, so it enters from here. The density of hot air is very low, so it actually leaves from the top. Okay. So this is the stack ventilation technique. And also we have the night ventilation. Suppose if you are living in a very hot region, what you have to do is that at night time you have to just open all your doors and windows and allow all the building elements, especially the walls and roofs, to cool for some time. Okay. So you should design a building in such a way that the building will be completely cooled during night time and should be ready to receive the radiation during the next daytime. Okay. So that is the night ventilation. Okay. You should cool the building completely at night so that it will be ready to receive the radiation during the next daytime. Okay. Otherwise, if you just close it, okay, and you use it next day, what happens? The heat gain inside the building or the temperature of the building elements further will increase because of the next day solar radiation. Okay. So evaporative cooling, as you might have already observed, this kind of cooling system is most popular in dry areas, not the coastal areas. Okay. So where the humidity is maximum. Okay. So this evaporative cooling is one of the best techniques to use in the dry areas. Okay. So some buildings will come with the pools, okay, fountains. Okay. So such kind of techniques, actually what actually happens here, the just air flows and takes the water, like first layer, like it is just like evaporation process. It just take the surface of the water, small latent heat. Okay. It will take from the surface of the water and leaves. Okay. As a result, when it continuously happens, what happens? The water surface temperature will reduce. Okay. Water surface temperature will reduce. When the air comes in contact, like nth time, maybe 100th time, that time you will be receiving the cold air inside the room. Okay. So this is actually what happens in the evaporative cooling. Okay. That is the reason why you feel to jump into the swimming pool during a hot sunny day. Okay. Hot sunny day temperature is same, but when you jump into the swimming pool, you feel comfortable. What is the reason? Because the temperature of the water in the swimming pool is colder than the atmospheric temperature because of the evaporation process. Evaporation is taking place there. So we also have solar roof pond techniques where we can actually have the water pond over the terrace, or we can say the roof. Okay. So this also can be used for both cooling and heating of the buildings together. Okay. Suppose if you are using this solar roof pond technique for cooling of the building, then what you need to do, you just have to take the water on the roof. Okay. And you just have to, this is the insulation, you have to remove this insulation and you have to expose this water to the night atmosphere. Okay. So when you expose this water to the night atmosphere, then what happens? Obviously, there will be the evaporation will be there. And also there will be the radiation. What kind of radiation at night? Sun will not be there. Then what kind of radiation will happen? So we know from thermodynamics that any body which is above absolute zero temperature will radiate heat. Okay. Here the water will also radiate heat. To what? So if you see the sky, stratosphere will be maintained at minus 30 degrees centigrade at night time. Okay. So as a result, the radiation takes place from this water to the stratosphere. Okay. As a result, this water will be losing the water. The water will be losing the heat, or it will be reducing its temperature. Okay. So during daytime, what happens? You just close the insulation. Since the water will be chilled for some time during the day, you'll feel comfortable inside the building. Okay. Suppose if you want to use this solar roof pond technique for heating of the building, the same technique can be used, but you have to expose this water to the radiation during daytime. Okay. For cooling, you expose the water during nighttime. for heating, you have to expose the water to the atmosphere during daytime. During daytime, when you expose it to the atmosphere, what happens? Because of the solar radiation, this water will be heated up. Okay. After that, we close the insulation. As a result, we'll be maintaining the warm temperature inside the building. Okay. So with this modified techniques also we can use, like we can actually sprinkle the water to increase the evaporation process and all. Okay. So you can see here without spray and with spray, various combinations you can see here. So this is the advanced solar roof pond techniques again. Okay. So we have again earth cooling techniques. So these all are like solar passive techniques. We are not using any kind of energy here. Are we spending any energy for maintaining the cooling? No, we are not spending. That's why we are calling it as solar passive. Okay. So here another technique we have, that is earth cooling. Okay. So here there is a building. Okay. So what we do, earth has got the best property. Okay. If you just dig inside the earth, if you go 3 to 5 meters depth inside the earth, there will be the constant temperature. Okay. The temperature will be ranging from 24 to 26 degrees centigrade, which is the most comfortable temperature for human beings in an air conditioned room. Okay. So just imagine, inside the earth there will be constant temperature irrespective of the season outside. You may be having the summer season, you may be having the winter season. Okay. Irrespective of the season, you'll be having a constant temperature inside. Okay. So what you do, you just have to take the outside air, you just have to blow it. Okay. Okay. Through this duct system and get the cold or comfortable air here. Okay. Earth cooling system is also there. Here you can see how it actually works. Okay. We take the air. Okay. So we'll be sending it through this tunnel. Okay. To the building, wherever you want to supply. Okay. So similarly, we have radiative cooling techniques as well. Okay. So where we have a nocturnal cooling, even olden days, the people used to produce ice when there were no refrigerators and all, with the help of nocturnal cooling, radiative cooling, what we discussed just now. Okay. Because of the stratosphere minus 30 degrees centigrade, we are able to cool the water. Okay. Even they used to produce the ice with that technique. Okay. So this is another technique. The another technique that we have is radiative cool paints. Okay. So radiative cool paints plays very, very important role. Just by applying paints over the terrace or paints over the roofs or walls, you are able to reduce the heat gain into the building. How that happens? So you know, we know this very well. If you wear a white shirt during a hot sunny day, you feel comfortable. Okay. If you wear a black shirt during a sunny day, you feel uncomfortable. Okay. Because the most of the radiation falling on the white surface will be reflected back to the atmosphere. Okay. So a lot of research can be done on this area by including many nanomaterials in the paints, and also recently we have a paper where they actually produce the papers, cool papers. What they have to do, just they have to remove the sticker backside and they have to paste it on the wall or roof. They'll feel comfortable. Okay. So recently one paper is published in ACS as well. Okay. So such kind of techniques, such kind of material, like if you add silicon dioxide and hafnium dioxide, okay, so then you can reduce the roof temperature by 5 to 10 degrees centigrade. Okay. This is a radiative cool paint technique. Okay. And also, like suppose if you don't want to have conventional air conditioner in your house. Okay. Because conventional air conditioner will actually consume lot of power. Okay. Common man cannot afford it. Okay. So then we can actually go for radiant cooling systems. Okay. So this radiant cooling system is nothing but it is the integral part of the walls and roofs. So we are going to have some pipes within the walls and roofs. Okay. Suppose if you see what is the difference between the conventional air conditioning system and radiant cooling system. So in conventional air conditioning system, we are going to use air. Okay, we are going to use air, means you will be cooling, you will be taking huge amount of air and cooling and sending it into the room to be cooled. But here what we do, see, if you take water, it is 832 times denser than air. Okay, and it has got a 4 times higher heat capacity than the air. Okay, so means to produce 100 ton of refrigeration, okay, you need 40,000 CFM of air, whereas you need only 32 CFM of water. Okay. So means cooling of the water is easier than the cooling of the air. That is what I am saying here. Okay. So this radiant cooling system works on that principle. Okay. So you will be using the water. Okay. what you have to do, this is the very simple technique. You'll just have to chill the water, okay, and circulate the water wherever you want. Suppose if you just put this lines inside the roof, you can keep it either inside the roofs or inside the walls or inside the ground as well. Okay, you'll just be circulating the water, okay, to these pipelines. Okay, so what happens actually? Why are we calling it as radiant cooling system? Okay, see, usually during the daytime, the hottest components inside the building are the roofs, walls, and of course the ground. Okay, so what we do, like as I already told, any body which is above absolute zero temperature will radiate heat. Here, these elements also will radiate heat inside the building. Okay, so because of this, what is actually happening? Uncomfortable conditions are produced inside the building. Okay, so if you circulate the cooled water or chilled water inside the walls and also the roofs, what actually happens? So you can feel comfortable inside the building. Okay, so you have to see, for example, in air conditioner, if you want to central air conditioner, if you want to maintain the water temperature, okay, maintain the water temperature in central air conditioner I am talking about, you have to chill it for 7 degrees centigrade. You have to chill the water for 7 degrees centigrade. Okay, but here you have to chill the water only for 16 degrees centigrade. Okay, 16 degrees centigrade. You will be circulating 60 degrees centigrade water to the building elements, okay, in order to get 24 to 26 degrees centigrade comfortable temperature inside the building. Okay, so this is it is energy efficient, cost effective thing we can say. Okay, so this system, like unlike conventional air conditioner, this system can be actually applied to whole building. Okay, so this is another advantage of radiant cooling system that we have. Okay, so another important aspect that we need to focus is on the envelopes. Okay, so when we talk about the envelopes, immediately the walls and roofs of the buildings will come into our mind. Okay, then how should be the wall? How should be the roof? What should be the thickness of the wall? What should be the thickness of the roof? What is the roof material and what is the wall material? So these things are very, very important to focus. Okay, so then what should be the wall thickness? Do you think if you have larger wall, you will feel comfortable? The people think that if you have a big thick wall, do you feel comfortable? Absolutely not. You don't feel comfortable with the thick wall. Okay, suppose if you have very thin wall, will you feel comfortable? No, absolutely not. You will not feel comfortable with thin wall as well. Then how should be the thickness of the wall? So thickness of the wall should be optimum. What is that optimum? As I already told, the wall thickness should be in such a way that it should receive maximum amount of solar radiation during daytime. It should absorb, it should store, and it should release all the absorbed solar radiation during nighttime to the atmosphere. Okay, means the walls and roofs should be ready to receive heat during the next day. Okay, so if you have very thick wall, what happens? It will be accumulated, heat will be accumulated inside. Lot of heat will be there, because as a result you will be getting uncomfortable conditions. Okay, suppose if you use a thin wall, then what happens? The solar radiation will directly enter into the room, again will provide uncomfortable conditions to you. Okay, so this wall thickness should be optimum. Okay, so what do you mean by optimum? So here there are two things which play major role. One is thermal mass and thermal insulation. Okay, so why do we need to focus on thermal mass and thermal insulation? Okay, what it actually signifies? Okay, so most of the people may be using thermocol. Okay, thermocol. Let us take two building examples here. So I made a building with only thermocol, a model building, let us assume. I made a building with thermocol alone. I made a building with only brick. I made a building with thermocol and I made a building with only brick. In which case you will feel comfortable? In which case you will feel comfortable? Will you feel comfortable with insulation building, like thermocol building, or you will feel comfortable in the brick building? Okay, this is very, very important thing. Okay, so they have got two best properties. As far as thermocol is concerned, it has got very good thermal insulation. As far as brick material is concerned, it has got very good thermal mass. Okay, thermal insulation means it can resist the flow of heat, but it cannot store the heat. Thermocol can resist the flow of heat, but it cannot store the heat. Whereas brick can store the heat, but it cannot resist the heat like thermocol, right? For our building, we need to have optimum thermal mass and also optimum thermal insulation. Okay. Suppose if you are using all together, means thermocol with brick, then you are going to just get the comfortable condition, right? So if you use thermocol alone, which doesn't have the thermal mass, it cannot store the heat. What do you mean by that? It cannot store. It can resist for some time. After some time, all heat will be inside the thermocol building. Okay. Similarly here, the brick you will feel obviously comfortable because it has got huge thermal mass in it. Okay. But if you use brick in combination with thermal insulation or thermocol, again you are going to get a better thermal comfort conditions inside the building. Okay. So this aspect is very, very important. Okay. So this thermal mass and thermal insulation can be defined by two parameters here. One is thermal admittance and thermal transmittance. Okay. So thermal transmittance should be as low as possible. Okay. And thermal admittance should be as high as possible in order to have, like, it is the best combination of, see, thermal transmittance and thermal admittance will talk about the combination of thermal mass and thermal insulation of any building material. Okay. So thermal transmittance should be as low as possible. Thermal admittance should be as high as possible. Okay. Right. How it plays major role in controlling room temperature. That is also very, very important. Okay. So what is the necessity? Why do you have to study? Okay. Right. So if you look at the building walls, as I told, so there are two parameters which actually define the thermal mass of the building. So decrement factor and time lag. Decrement factor and time lag. Okay. So how are we going to get this decrement factor and time lag? What is its significance? Okay. So let us take an example here. Suppose let us take the example of the wall here. Okay. So let us assume the outside temperature is 30 degrees centigrade, just for example's sake. Okay. Outside average temperature is 30 degrees centigrade. If the wall has got the decrement factor of 0.5, okay, it allows only 15 degrees centigrade temperature to the inside. Means 15 degrees centigrade temperature will be there inside the building. Means decrement factor is 0.5 here. Okay. Suppose if there is a decrement factor of 1, then what happens? 30 degree, here also you will have 30 degree. Means there is no wall at all in between. Okay. Or the wall is not sufficient. Okay. So decrement factor should be as low as possible. Okay. If it is 1, the same temperature will be there outside and inside. If it is less, then the temperature variation will be there. So decrement factor of the wall should be as low as possible. And this decrement factor is concerned with the time lag as well. Okay. So what should be the time lag? What do you mean by time lag? Okay. So this is the time, how much time the outside heat wave takes to reach inside. Okay. How much time the outside heat wave, peak outside heat wave will reach inside. Okay. So if it reaches, usually the 6 to 12 hours it should be. Okay. The time lag of any building material should be ranging from 6 to 12 hours. Okay. What happens if it exceeds 12 hours? So if it exceeds 12 hours, the heat will be added to the next day heat. For example, if you have designed a wall in such a way that the heat will be added maybe next, like suppose this maximum heat peak inside the building, if you are getting next day morning 10 a.m. What do you mean by that? Already you have started receiving the solar radiation. To that solar radiation, this heat will also be added. You will feel uncomfortable condition. That's why it should not exceed 12 hours. Okay. So time lag should be ranging from 6 to 12 hours. That is very, very important. Okay. So in order to obtain these properties, we consider one-dimensional diffusion equation. Why one-dimensional? Because there is a lot of temperature difference only across the thickness of the wall. Okay. So other direction, it is very, very small temperature difference. Okay. So when we solve this with the periodic convective boundary conditions, so we'll be getting the solution. Okay. When you arrange this solution in the matrix form, okay, it looks like this. Okay. And these terms have got some properties of the materials. Okay. So these properties of the material we have to explore for the building materials, what you are taking or what you are making. Okay. So you have to put these properties into the equation in order to get the other parameters, in particular What all are the parameters? So admittance, transmittance, time lag, and decrement factor. Okay. So if you look at these conditions, so here we have the wall. Okay. So it will have outside air resistance, inside air resistance will also be there. Okay. So if you want to keep this electrical circuit in the matrix form, it looks like this. See here, this matrix is for the air resistance outside, and this matrix is for the wall layer, maybe n number of layer. You can have any number of layer, isn't it, right? So this matrix is for this wall layer. Okay, this matrix is for the another wall if you are using. Okay, and this matrix is for the internal air resistance. Okay, so when you evaluate these things for the properties, then ultimately we'll be getting the cyclic transmittance, decrement factor, decremental time lag, and thermal admittance. Okay, so we call them as unsteady state thermal characteristics. Okay, so we can use those things and all in the mathematical programming in order to get the quick solution. Okay, so we tried unsteady state thermal characteristics for various materials, various Indian materials. I think we tried for all the Indian materials available in the SP41. Okay, so which is a good standard for the building energy calculations and all. So here we have tried for 10 building materials and 10 insulation materials. We can see here. Okay, so here what we can say here, we explored the properties, that is thermal conductivity, density, specific heat capacity, okay, diffusivity, all those properties we explored with an instrument. Okay, and later on what we have done, we actually computed the unsteady state characteristics such as transmittance, okay, decrement factor, time lag, admittance. Okay, so all these things we explored. So from the results what we observed is that, so among all building materials studied, if you can see here, so as I told, the decrement factor should be as low as possible, and the time lag should be as high as possible, and it should not exceed 12 hours. Okay, so here we have got for BM9, which is mud fusca. Okay, so we have got better decrement factor and better time lag values. So worst case we observed for the cinder concrete, where we got the highest decrement factor and the lowest time lag values. Okay, so similarly when we observed for, we studied this for individually for buildings and insulation materials, not together. Okay, so when we studied for the 10 insulation materials, starting from sawdust, rice husk, coir board, jute felt, jute fiber, coconut pit, okay, straw board, asbestos fiber, wall board, and chipboard. Okay, so we explored the unsteady state characteristics and found that IM6, that is coconut pit insulation, so has got the lowest decrement factor and the highest time lag value. Okay, green indicates the best and red indicates the worst condition. So here IM2, that which is the rice husk, which has got the highest decrement factor and the lowest time lag values. Okay, so with this we'll also come to know what should be the thickness of the wall in order to get the optimum thermal mass inside the building. Okay, so you cannot use whatever thickness you want. Okay, so you can ask, sir, suppose if I use a smaller thickness of the wall, then the building will collapse. You can ask this question also. Okay, so but it doesn't mean that if you use like a basic requirement, like whatever thickness of the wall, usually first of all, whatever buildings that we are constructing nowadays, load will not be on the walls. Okay, load will be on the columns, not on the walls. That should be clear. Okay, so walls nowadays, just they have become the partitions. Okay, so we use walls only for partitions, but still we maintain the required strength for the wall as well. Okay, we do not compromise in the strength as well. By maintaining the strength, we have to get the thermal comfort through those walls. That is our main objective of this kind of work. Okay, so here you can actually explore the optimum thicknesses of the building materials to be used inside the building. Okay, for this we also have coconut pitch insulation, where we are getting the least value of the thickness, and rice husk has got the maximum value. So here for this building material, slate has got the maximum thickness, and mud fusca has got the least thickness of the wall to be maintained. Okay, so in order to have the best properties out of it. Okay, so that is the thing. And here we can see the decrement factor, how the decrement factor is varying for various building materials. Okay, so mud fusca, you can see the decrement factor at 0.2 meters thickness is 0.501, which is actually found to be the best one. and cinder concrete we tried, and it is found to be 0.641, okay, and found to be the worst condition among the studied materials. Okay, so similarly we tried for the insulation material, where we found 0.024 decrement factor for coconut pitch insulation and 0.779 decrement factor for rice husk. Okay, so this is the worst condition and this is the best condition. So we also have the time lag values for rice husk. So 4.3 hours least time lag, coconut pitch less than 12 hours, that is 11.8 hours, again the best combination. Okay, so like this we have explored the materials and we have come up with the best solution for the materials, okay, available in Indian market. So like this we tried around total 20 Indian homogeneous building and insulating materials we tried. Okay, and order, most energy efficient order. Okay, so we have given preference according to the energy efficiency what we are getting from the building material. The first one indicates the first preference and the last one indicates the less energy efficient performance. Okay, similarly for the insulation material you can see the most energy efficient order to the less energy efficient. Okay, so another important concept nowadays we are going, so far we have seen like building insulation materials can be used, okay, in order to have energy efficiency in the buildings. Okay, so now another important topic, it has become now very advanced topic in the research and development, the use of phase change material in building enclosures. Okay, so why do we have to use phase change materials? Okay, the name itself is explanatory. Phase change material, it changes phase when it absorbs heat. Okay, so when it changes phase when it actually releases heat. Okay, so you might have observed, especially practically you might have observed for data centers, the AC, air conditioning system is mandatory. Okay, so if you do not have the air conditioning system for some time, maybe for half an hour or 1 hour also, that will affect the electronic components. Okay, so in such places they use phase change material. Why? What is the reason? Suppose there is a, let us assume there is a data center. If there is a power cut for, let us say, half an hour, okay, if there is a power cut for half an hour, what happens? The cooling load will increase like anything inside the building, inside the data center. Okay, so if they use phase change material for the inside walls and roofs, then what happens is that this phase change material will absorb the heat. You switch off the air conditioner, obviously the electronic component, data center, all those things will be releasing, all the electronic components will be releasing the heat. That heat will be absorbed by this phase change material and changes its phase. It stores in it. Okay, so as a result, because of this phase change material inside the data center walls, okay, so you can maintain the cooling for some more time, maybe for 1 hour, 1.5 hours. Okay, you can extend the time. By that time you can actually get the power back. Okay, so means the storage of heat plays very important role. When it absorbs heat, okay, when the AC is running, that time it will be in the solid state. Phase change material will be in the solid state. When it absorbs heat, it becomes the liquid, okay, and it stores the heat, whatever heat released by the electronic component, it absorbs and holds it in it. Okay, so we tried for the buildings, especially for the buildings, the most acceptable melting point of the phase change material is less than 30 degrees centigrade. If you use less than 30 degrees centigrade, it is advantageous, but we tried with the 35-46 as well, okay, in order to see the performance. Okay, so we tried with 5 different phase change material, hydrated salts of melting point 24 degrees centigrade, organic mixtures of melting point 21, 30, 35 and 46. Okay, and we explored their properties, thermal conductivity in solid state and also in the liquid state. Okay, and also we explored their specific heat capacity, okay, in solid and liquid state both together, and also we measured the solid and liquid density of the PCMs. Okay, so this is the experimental setup for measuring thermal conductivity, okay, what we have used, which is available in V80 Vellur. Okay, so this is the model which we considered here. So you can see here, this is the configuration, building configuration. This is conventional one. There is a concrete block and plaster both sides. Okay, and this is the wall with PCM. Okay, we have used PCM at the center here. Okay, and if you look at the other view of this particular configuration, it looks like this. So this is the PCM layer. Okay, so you cannot directly keep the PCM because it is changing the phase from solid to liquid or liquid to solid. Okay, so you have to use some containers. Okay, either plastic containers or aluminum containers. You should use them as enclosing materials. Okay, otherwise what happens when it changes its phase, then simply the PCM will go off. Okay, so this is the things, these are the dimensions what we have considered for this study. Okay, so here we observed, again we computed the time lag and decrement factor both in solid phase and the liquid phase together, and we calculated the average value. Okay, so from this we came to know that the OM30, okay, is actually giving the highest time lag value, okay, and the lowest decrement factor. Okay, so similarly, see, this time lag and decrement factor are very, very important, especially if you are using it for, if you are using the building for non-air conditioned building. Okay, so it is just like suppose if you are using in office buildings. Okay, so if heat comes inside the building during night time, no problem, because night time no one will be there in office. Okay, but at least when the occupants are there inside the office, they'll feel comfortable. Okay, so these time lag and decrement factors are very, very important for free reign buildings as well as such as non-air conditioned buildings. Okay, so we can see the performance of this PCM integrated buildings as well. Okay, suppose if you are using it for the air conditioned building, suppose by using this PCM integrated walls or roofs, how much amount of energy you are going to save if you are using an air conditioner. Okay, for that we have different approach, as I have already told. This approach is not constant. This approach changes place to place. Okay, because the sun earth geometry is very, very important. Okay, so when sun earth geometry plays very, very important role, we need to consider various angles, sun geometrical angles, solar altitude angle, declination angle, solar azimuthal angle, surface solar azimuthal angles. Okay, and we also have to actually compute how much amount of radiation is falling on the wall, falling on the roof. Okay, so we have to compute. Okay, so that too, all the radiation, what kind of radiation, direct radiation, diffuse radiation, and ground reflected radiation. Okay, so you have to compute, or you can also measure it in practice. Okay, so pyranometer, with the help of pyranometer, with the help of thermocouples and all, you can measure the temperature and also the radiation accordingly in practice. So I am just showing the numerical methods how to attain the direct radiation, diffuse radiation, and ground reflected radiation, which constitute the solar radiation. Total solar radiation is the combination of all these three. Later on, the solid temperature is very, very important. Okay, so solid temperature will be having the main component, that is radiation. Okay, so radiation component, so there is absorptivity component is there. Okay, H0, and also the outside temperature. Okay, so from that we will be calculating the heat gain inside the building. Okay, so air conditioning cost is depending on this, right? So what we are doing here, we are actually finding out the reduced cooling cost. Okay, reduced cooling load or increased cooling cost. Okay, so reduced cooling load or increased cooling cost. Okay, this value. Okay, so this one is reduced heating load or increased heating cost. Okay, so we are going to compute later on. So you are spending some amount for PCM. Okay, so when will you get that amount back in terms of energy savings? That can be denoted by the payback period. Okay, we have to compute the payback period. Okay, so later on, by saving this much of energy, how much amount of carbon emission reduction that you are doing. So ultimately, as I told, greenhouse gas emission plays very, very important role. If you are not able to control greenhouse gas emissions, we know very well what kind of natural calamities are going to take place. Okay, so greenhouse gas emission is very, very important here. Okay, so we did for two climatic conditions here. You can see, you can take the example of New Delhi and Jodhpur. Okay, so both are two different climatic conditions. In New Delhi, so there is extreme cold during winter and there is extreme hotness during the summer. Okay, so Jodhpur, it is completely hot and dry. Okay, where you find no heating requirement. There won't be any heating requirement in case of the Jodhpur climatic conditions. Okay, so these are the parameters what we consider: price of the PCMs available in the market, and we explore the thermal conductivity of other things. Okay, plaster, annual cooling degree hours. okay, annual heating degree Hertz, okay. So outside heat transfer coefficient, inside heat transfer coefficient, okay, coefficient of performance for the worst. Suppose if you are using the low performing air conditioner, okay, then how much will be the COP? Why we have assumed the worst case? Because we are testing it for worst case. Unit cost of electricity, unit cost of natural gas for heating, okay, efficiency of the heater, okay, mass of the carbon emission rate per unit usage of electricity, all those things we consider the parameters, okay. So we also observed the effect of wall orientation, okay, for various places for Delhi, okay. A is showing for Delhi and B is showing for Jodhpur. So here also you can see here what we studied, what we understood from the concepts. So south is the best direction, okay. So that is clearly visible here. Here also for the Delhi, the south in summer, it is going to get the lowest heat gain, okay. And here for winter we are going to get the maximum heat gain inside the building, okay. So that is also actually the requirement, okay. This graph is as per the requirement, okay. So this is for Jodhpur conditions, okay. So from this you will come to know which one is the best orientation. No doubt, without any no doubt, you have to avoid placing the windows in east and west direction. You must prefer placing the windows in north and south direction, okay. So that will be the best solution in order to get the best result out of it. Okay, so here again we calculated for total heat gain, how much will be the total heat gain, okay, through building envelope and all, okay, for Jodhpur, and also we have done it for the New Delhi climatic condition. So this side on y-axis you can see incident radiation. So left side you can see passing radiation, incident radiation and passing radiation, okay. So accordingly you can see here the OM30 is actually getting lower heat gain, okay. So lowest heat gain. So that is also very, very important. So we have arranged that the order again, the best to worst, okay. So annual energy cost saving we computed for integrated building models, what we have considered, okay. So here you can see we considered again 5 PCMs. Here you can see from the graph you will come to know that air conditioning cost saving. So this should be as high as possible. So here OM30 is giving the best air conditioning cost saving aspects, okay. So, and HS24 is giving the worst performing here, okay. So payback period, as you know, the payback period we need to include initial cost of the PCM as well. So PCM cost varies from PCM to PCM, that also we have to take into consideration, okay. So here payback period is highest for OM30 because of its high initial cost, okay. So if you can see, if you take the payback period into the consideration, then the best performing, see, payback period should be as low as possible, okay. So that should be OM35 is the best from the payback period aspect, okay. So these are the things, and also we have computed carbon emission reduction for various PCM integrated building enclosures, okay. So from this we came to know that emission reduction is maximum in case of OM30, okay, and it is the least in case of the HS24, okay. So the summary of this particular thing, the best order of PCM for both non-air conditioned and air conditioned buildings, okay, from all the parameters studied perspective, you can arrange them from the best to worst. The best is OM30, okay, followed by the OM21, OM35, OM46, and HS24 is the worst performing PCM here in this particular study, okay. From an overall perspective, the organic mixture OM30, okay, is found to be the best from lowest decrement factor point of view, the highest time lag point of view, and also the energy saving and payback period, highest carbon dioxide emission point of view, okay. So this is the summary what we have drawn, okay. So another building enclosure what we need to focus, this is another important thing, so which is glazing, okay. Why do you have to put much focus on glazing? Okay, see, if you have walls, no problem, it will take some time for getting the heat gain into the building because the wall has got some thermal mass in it, okay. But glazing is not like that. If you put glazing or glass, window glass, what happens? The solar radiation will directly enter into the room. There is no thermal mass in the glazing, okay. Directly it will enter into the building. So we need to focus very much on glazing, especially for the commercial buildings, okay. Nowadays most of the commercial building, if you go to any metropolitan cities, you see all glass buildings with air conditioner on inside it, okay. So if when you use that much extensive amount of glazing, then it is very essential to focus on glazing part as well, okay. So there are different glazings, okay, and also if you see how to evaluate the properties of glazing, okay, so if you see the solar radiation wavelength, okay, so solar radiation from sun to earth travels in electromagnetic waves, okay, and it has got some range from 280 to 4000 nanometer, okay. So if you take only small range, maybe 280 to 380, so that is ultraviolet, so there will be only 2 to 3% radiation, okay. So ultraviolet spectrum will contribute to only 2 to 3% radiation. So if you talk about the visible spectrum, so it contributes to 47% radiation only, means UV and visible together will give you 50% radiation, okay. So when you have to consider the total radiation, because see, you are using the glazing for heat gain, okay. When you are using it for heat gain, you have to consider the total radiation 100%, means you have to consider for the infrared as well, okay. So infrared goes to 4000 nanometer, but near infrared, up to near infrared will fetch us the maximum 98 to 100% radiation in it, okay. So when you test the glazing for the solar spectral properties, okay, so these things are very, very important. Suppose if you want to study only for visible performance, okay, glass can be used for two purposes here. One is for daylighting, another is for saving the energy and aesthetic appearance, okay. So from our aspect, we are going to use it for daylighting and also for reducing heat gain, okay. So when you are evaluating the glass for daylighting factor, then we need to consider only these two spectrums, okay. So because we need only visible spectrum, the name itself is explanatory, visible, okay. So daylighting performance we are going to evaluate for the visible spectrum, UV visible spectrum, up to here only. So when you are talking about total heat gain, when you are talking about complete solar heat gain, okay, then you need to consider all together, which will constitute 100% radiation, okay. So this is very, very important point to be considered when we are evaluating the properties. We have got so many types of glazings: clear glazing, tinted glazings, okay, where we use the metal oxide directly into the molten glass, okay. Reflective glazing, where we use reflective coatings on the glazing, on the conventional glazing. Double glazing, where between the two conventional glazing will maintain the air gap. Triple glazing, between the three panes of the glazing we are going to maintain the air gap. Laminated glazing, so we'll have a sandwich of layer between the two layers. Glass bricks, they have become very popular nowadays, okay. So glass bricks, which will actually give a lot of daylight factor and also reduce the heat gain into the building. Photochromic glazing, these glazings are very popular, especially for the spectacles which changes color with respect to the solar radiation outside, okay. The problem with the photochromic is that they are very costly, we cannot afford it for the buildings. For buildings, the glazing should be as low as possible cost, okay. So if it is very costly, then we cannot afford it. Photochromic is very, very costly glazing, we cannot afford it for the buildings, okay. And we also have got the smart glazings, where we will be dealing with the polymer dispersed liquid crystal glazings, and also we will be dealing with the gasochromic glazing, okay. So among all glazing, actually I have presented our own work for the PDLC, which comes under the smart glazing. So that is polymer dispersed liquid crystal film glazing, okay. So here the beauty of glazing, this glazing is very, very popular even nowadays. The best cars in the market, the costliest car in the market, especially BMW and Mercedes Benz, so those cars also, they are using this kind of smart glazing, okay. So what is the smart glazing? We can also call it as switchable glazing, okay. So how it looks, see, it looks like this. So it will be completely, we can say, here you can say it is not completely opaque, at least we cannot see what is inside, okay. So when you switch on, so when you give electricity, that will become transparent like this, okay. When you stop giving electricity, it becomes like this, blurred, or we can say it is not completely opaque as well, it's not opaque, okay. So but what is going on inside, it cannot be seen, okay. But when you switch on the electricity, yes, you can switch. So we tried with the various colors, okay, of polymer dispersed liquid crystal films, okay. So here you can see the blurred version, and here you can see the transparent version, okay. So these glasses are very popular in the popular automotives, okay. So we applied this for the buildings, okay. So actually they also need, see, you have to supply electricity for changing this state to this state. Okay, how it happens? You have to supply electricity. Who will supply that electricity? That is also very, very important. By supplying this electricity, are you able to save any kind of cooling load with that? That is also very, very challenging. Okay, but what we observed from these studies is that the energy that we are going to save with this glazing is very, very, very high as compared to the energy spent on this glazing. Okay, so that is the best observation what we made from this. Okay, so we tried this for different glazings, and we explored the solar optical properties with the help of the experimental setups, okay, that we have in VAT Vellur. Okay, so here you can see the spectral transmission graph. Here you can see the spectral reflection graph. Okay, for blue smart PDLC film glazing. Okay, you can see here. So transmission, as I told, this transmission should be for complete solar spectrum up to near infrared, that is 2500. Okay, so that should be very, very important. See here, the solar transmission is very, very high for clear glazing. See here, in all spectrums, starting from UV visible to the near infrared, all the spectrum transmission is very, very high as compared to this. Okay, so reflection also here, reflection you can see here, the clear glazing is not able to reflect much, but our glazing, smart glazing, is able to reflect most of the radiation back to the atmosphere again. Okay, so this is the case for even the pink colored smart PDLC film glass and the yellow colored smart PDLC film glass, and also white colored smart PDLC film glass. Okay, so we explored the properties. So we need to get ultimately 3 properties: solar transmittance, solar reflection, and also solar absorption. Okay, so these things are very, very important. We tabulated the properties. Okay, so from the results we observed that, see, clear glass has got the maximum transmission, that is 77. Okay, and solar heat gain, if you see, so that is 81. A lot of solar heat gain, lot of transmission. But pink smart PDLC, if you see, it has got less transmission. Okay, and it has got less solar heat gain coefficient. Okay, so with respect to heat gain, yes, the results are fine. Now another important thing that we need to consider is that, okay, if you completely block the glass, you'll feel comfortable inside. Okay, but another aspect is there: are you able to get the ample of daylighting inside just by blocking the glass? That is also very, very important point to be considered. Okay, our main objective is to reduce cooling load by maintaining adequate or required daylight factor inside the building. Usually the daylight factor should be more than 1.2 for most of the buildings. For most of the buildings, if you have 1.2 daylight factor, then it is actually the good one. Okay, so whatever glazing you are trying or whatever glazing that you are making, you should see that it should actually reduce the heat gain, as well as it should give ample of daylight factor value inside the building. That should be the objective. Okay, so we considered the building models here, different models. Okay, and we explored this for ultimately how much amount of cooling cost that we are going to save. We compared all these glazings with respect to clear glazing. Okay, so how much amount of air conditioning cost we are going to save with respect to the conventional glazing. Okay, so here you can see the heat gain through various smart glasses. Okay, so if you can see with respect to the orientation, you can see here. Okay, so here we consider 8 orientation, unlike 4 orientation. Earlier we considered 4 orientation, here we consider 8 orientation. Okay, and also the daylight factor, as I told, see, clear glazing has got, obviously clear glazing has got more daylight factor. Okay, so too much daylight factor also we don't need. If you have too much daylight factor, that will actually give you glare kind of effect for you, and also it will also give you like a lot of heat gain inside the building. Okay, too much daylighting factor is also not required, but the required daylight factor must be maintained. That should be our main objective. Okay, so if you look at all the glazings what we studied, we are able to get the daylight factor for almost like for almost all glazing we are able to get more than 1 daylight factor. Okay, more than 1 daylight factor, which is actually the results are favorable. Okay, so we can say, so these things are also very, very important. So you can see air conditioning cost savings, you can see for various glazings. Okay, with voltage on, with voltage off conditions, you can see here. So for various orientations, again 8 orientations you can see. Okay, so from the graph we can say that we are able to save more amount of energy Okay, so with respect to various glazing systems of the smart. Okay, so here you can see the best order for the glazing system. So white colored one, okay, next blue colored one, okay, yellow colored one, and pink colored one with respect to voltage applied condition. Okay, so payback period cost usually it is 12.7 years here. Okay, so okay, that is also feasible conditions that we are getting. Okay, so what we found here, it is recommended to place smart window in southeast orientation. Okay, so we observed here southeast, southwest, and south related orientations are best orientations to place this glazing systems. Okay, so that is also very, very important. And it is not recommended, especially northeast, northwest orientations are not at all recommended for placing the window. Okay, in order to reduce cost savings. Okay, so these are the things. Okay, so we observed that like solar transmittance of white PDLC, okay, that is 85.71% less when compared to the conventional glazing, okay, with adequate daylight factor. Actually, these things are very favorable results. Okay, so these are the various systems that we have. Okay, so these are the references what we have. And go green, thank you. I would like to take the questions from your audience. Thank you very much.
Dear audience, now it's your turn. You can ask any kind of doubts.
Hello.
Good morning, sir.
Sir, very good morning, Saboor sir. It was a really
I am on
very
Answers
nice topic
Mukram.
and interesting topic, and really it's nice presentation.
Thank you, Dr. Parsham sir. I hope you are doing good.
Yeah, sir. Hope from your side also. Same.
Yes, thank you, sir.
Yes, sir. It was a nice topic. Just I wanted to convey you, like it was presentation was very good, and I mean topic also very nice. Just I do have one query. It's not technical query. Just I wanted to know from your side, like as the trend of Indian people, like generally will see the vastus, right? So what is
Yes.
your opinion with respect to vastu and the technology for this glazing of the, I mean glazing factor?
Yes, I think yes. Yes, sir. Is it completed, sir? Your question completed?
Yes, sir. Yes, sir. Thank you.
Yes. So that is actually a very good question as far as Indian aspect is concerned. So Vastu, we haven't considered in our studies. As far as our studies are concerned, technically we have done for all the technical aspects. Yes, so these studies, especially for these studies, as by considering Vastu can also be carried out. But that result will not be useful for the global exposure. But for Indian aspect, we can consider it and we can explore these things as well.
Yeah, thank you.
Thank you,
Saboor
sir. Thank you very much.
Yeah, and at the same time, I would like to thank Sriji sir as well as Vignesh Nayak sir and the Department of Mechanical Engineering AG IET for providing such a platform during this pandemic situation. Take care, everyone. Thank you, sir. Thank you.
Thank you, sir. Thank you very much.
Good morning, sir.
Yes, good morning, professor. Please.
I am Anfas, working in Yanapa Institute, Mudibudri.
Hello, sir.
I have a question regarding this. For this building performance analysis, we are using lot of software tools.
Yes.
Do you have any suggestion regarding that? Which tools we can use for the analysis, especially considering the building fabric, wall or just like glazing material? You can suggest any software tools for that?
Sure, sir. Sure, sir. So there are many softwares. We have Energy Plus, Design Builder. There is a Ecotech analysis, and we also have Transys. In Transys, also some simulations can be carried out. So these are the various softwares, most often used softwares, what I can say. So Design Builder, Energy Plus, and Ecotech analysis. And sometimes we can also use Transys as well. I hope I have answered your question, sir.
Yes, sir, sir, definitely.
Yes, thank you, sir.
Okay. Sir, this your work is published, I think. Can you give the reference for that? What
Sure,
is your secondary year?
sure. Definitely, I'll share some of my reference papers to you, sir. I think I'll share it to Dr. Srijit, and Dr. Srijit will distribute it to everyone.
Okay, sir.
Sure,
Thank
I'll
you.
do it.
Thank you. Sir, one more thing is, sir, glazing materials you are telling regarding smart materials. Sir.
Yes.
Can we combine glazing with the PCM materials? Is it possible?
Yes. I think those studies also we have carried out, but we haven't put it in this particular topic. So we tried with the phase change material. So instead of air, we actually replaced the air with the phase change material, and we saw the performance, and we reported also that study. But we haven't shown it here in this presentation.
Can you tell which material used? Can you phase change material for that?
So we tried with around 4 to 5 phase change materials. We tried with 4 to 5 phase change materials. Again, we are able to get two best materials. One is HS24 and another one is OM30. Okay, because see, when we are talking about glazing, we have to consider transmission also.
Yes,
how
yes.
much heat is actually transmitted.
Transparency
So,
also.
yes, it is unlike the wall. Wall will not have any direct solar radiation entering into the building. So we have to consider the transmission also. Means we need to explore properties for it. So we need to consider heat gain through radiation, conduction, and also convection. All these things together.
Okay. So commercial materials are suitable as per your opinion. Commercial.
Yes,
PCM.
yes. Most of the PCM materials are suitable, sir. Most of them. But we have to explore unless we explore their properties, we'll not come to know which one is the best one.
Okay, sir. Okay, sir.
Thank you, sir.
Anyone else has any queries? I believe everybody is very happy with the presentation. So I now request Dr. Srijit VK to render the vote of thanks.
Thank you, Harold, sir. I'm Dr. Sheik VK. First of all, a warm and cherished morning to our most valued honorable resource person, Dr. Sheik, Saboor, participants, and all my fellow workers joined with FDP. Before actually I move into my the vote of thanks session, I want to tell something related to the presentation. I really actually got enlightened, I can say like that, by the way of this presentation. So main thing I want to tell about today's presentation are the way how he conveyed the information and the depth up to which he went, and the different disciplines or different areas in this particular thing. He started from a very basic thing, and like in a sense, in the first few slides, if any common people sits here, they can understand, they can directly implement those ideas if they are constructing their own building, house or something like that. And after that, he moved to the technical side, which would be most helpful for people like us who are doing research or who are doing the just going to join the research PhD and all that kind of thing. So it contains both direct information passing to the common people as well as the technical information passing those who the PhD aspirant or research aspirants. So I really want to congratulate on all this aspect to our Sheik Saboor sir. Now I move to my duty. So it's my privilege to propose a vote of thanks and acknowledgement to the one and all present here. First of all, on behalf of my department and all HIT family, A wholeheartedly thanks our resource person Dr. Sheik Saboor, who spent his busiest time gracing this occasion and sharing a valuable information with us. Today, we had an opportunity to hear your experience in research as well as the stream of knowledge in the area of efficiently building concept. I'm sure the session inspired the research ideas of many of our participants gathered here. I would like to thank all the participants of our FDP who have joined on time and made it very interactive session, and that made it a very big success. Finally, I would like to extend my sincere thanks and appreciation to all the people who have been working behind the scene to achieve this event. Once again, thank you everyone, and we shall wind up today's session, and we will come back tomorrow with our fifth day of FTP, which will be handled by Dr. Samsundar from National Institute of Engineering, Mysuru. And I request all the members to join on time, and like this today's session, make that session also a grand success. Thank you all.
Thank you, Dr. Srijit, for your kind words. I would like to thank Dr. Vignesh Nayak and also Dr. Srijit and the management of AJ Institute of Technology for giving me the opportunity. Thank you very much, and have a great day.
Thanks.
Thank you very much.